All right, let's do a sound check if we can settle down a bit, folks. Thank you. Can you hear me back there? Can you hear me back there? Excellent. I thought I'd start by doing a little bit of sort of what the Army likes to call after-action analysis on the test we just finished. And before I discuss the specifics of it, I want to introduce you to something that's been going on maybe behind the scenes in all the courses you're taking, which is that the exam center provides to professors who want it statistics about the test that really give you a great deal of information about it. And two numbers that are especially relevant are a number called difficulty, which is simply the percent of students who get that particular question right, and something called discrimination, which is a number that says to what extent do students who get other things right get this right. Obviously, if there's no relationship between doing well on the test and that question, it's probably not a very good question. And if you have the horrorest nightmare of having a negative discrimination, you really know you're in trouble. I don't think I've ever had a negative discrimination so far. Those numbers are also available for each individual choice within the question, and so I can go in and look and say, oh, that's the common mistake that people tended to make. So it allows us to analyze things in some detail, and I thought you might want to see what some of the conclusions from all that was. Let's see. There were two questions in which we accepted two answers. We told the exam service up front, please accept both of these as correct answers for these questions. One was question 25 on Form A, which is not true of lipids. A student with more botany background than me wrote to say, well, cutin is a polymerized lipid, is this wrong? And I went to look at the structure and dag-nabbit, it's a polymerized lipid. So I learned something. So we were accepting both answers, despite the fact that on answer D, people apparently were mostly guessing by the statistics. So several people lucked out on that one. I can't take points off for a correct answer. I'm just not built that way. Collagen, there were discussions of this before. People were in some confusion about collagen polypeptide versus collagen bundle and so on. So we decided to accept both D and F. That was done at the level of going into the exam service beforehand. There was one question that turned out to be basically a useless question, and I apologize for having written a useless question. This had essentially it had a random answer. It had a discrimination close to zero and small fraction correct. So I'm not quite sure why a question that has the right answer caused such confusion. Maybe it's because there was a conflicting definition in the textbook. I did want to point out a couple of answers that are clearly wrong. A segment of DNA that encodes a protein is not a general definition of a gene, because many genes don't produce proteins. Just to take some examples, the genes for ribosomal RNAs produce RNAs. They don't produce proteins. It might have seemed that a region of DNA that has a product which affects the cell would be a general definition, but there are also genes, meaning stretches of genetic information, that have a phenotype that have no product at all. And so that is not, strictly speaking, a correct answer either. I think A confused some people because they wanted to say, well, one gene may not be enough to determine a trait. Anyhow, we're throwing the question out. Rational. I could be reasoned with. This was one that had a very good discrimination, meaning students who understood the rest of the stuff got it right, but it apparently was harder than the other questions. And a common error was to think that the hydrogen bonding interactions were limits to the conformation. But if you think about it rolling around and tumbling in space, it's not the hydrogen bonds that limit it from exploring all of conformation space. The hydrogen bonds stabilize the final conformation, but they are not, in fact, a constraint on what things are explored. Another one that, again, had a good discrimination, meaning students who knew the rest of the stuff often got this right, but still was more difficult than I expected, was this one. And the a common error was to only recognize the oxygen binding at one heme site as an allosteric behavior. BPG binds at the interior of the hemoglobin tetramer. So if it's binding at the interior, changing affinity, that's an allosteric effect. And what's especially sort of striking about this one being more difficult than I expected is that 2 questions above it is one about the BPG pocket, and 87% of the students got that right. So you knew that it was there, but it somehow or other didn't transfer to this question. Common error here was to think that stacking interactions can enhance proteins, stabilize proteins. Stacking interactions are the pi orbital interactions between nucleotides and nucleic acids. And to the best of my knowledge, there are no examples of stacking interactions in proteins. Susan, who is a structural biochemist and knows in some things more about some of these things than I do, says she's seen some examples where 2 side chains may have pi resonances, but nothing where you could say it's a general pattern or where it contributes more than a small percentage to the overall packing. Since there's clearly one question that has to be thrown out altogether and several that were harder than I expected them to be, I'm going to adjust what the cutoffs for grades are for this test. So 80 and above will be an A, 70 to 80 will be a B, 55 to 70 will be a C. And I'll probably do that by, at the end of it, subtracting those points from the aggregate of 500 before I do the math, but this should give you a sense of where you are. Any other questions about the test or about grading or anything like that? I try to be rational. I just want you to learn. I would love to have to go to the dean and say, yes, I gave 90% of my students A's. Nothing would make me happier. Yes? The student is still grading those, okay? And I'm trying to remember what it was. It was about a threonine for a serine versus a lysine for a histidine. Is that right? If you think about it, in an active site, a threonine is a fairly conservative change for a serine and can probably do the same chemistry, but might be sterically a problem. Whereas lysine for histidine, the lysine will always be protonated on top of the fact that it's a different shape, and so it would be more likely to be affect the activity. So, any other questions about the test or about the exam service? Is that a question? Okay. Question. I only threw out one, the one that had essentially a random answer to it. I was looking sort of at the aggregate of the level of difficulty, and that's what I based the further adjustments to, but I can't really point at one specific question and say it's this one that made me do it. Okay? Excuse me? The question that's being thrown out is wrapped into that 10-point correction, okay? Does that make sense? So 7 points of that is overall difficulty of the test, 3 points of that is due to the question being thrown out. Okay? Any other questions? Okay. All right. So, let's talk some science. I hope some of you enjoyed that PowerPoint of the powers of 10, and that will be available on the website also. I don't know if you've noticed this, but when I have those slideshows for your enjoyment and relaxation, they're also available off the website. So before I get too far into kinetics itself, do people have any other questions about enzyme mechanisms, about the ways that we talked about how enzymes act before we get into the kinetics? Okay. The whole body of enzyme kinetics came about because it's at least as important not just to know how an enzyme works, but also to know how fast it works. And what the whole mathematics of kinetics is going to be able to do is to give us numbers for speed, how quickly it turns over with a substrate in it, and specificity, how well it holds on to a substrate. This is sort of analogous, if you think about it, back in the distant past when we were talking about enzyme mechanisms, that the active site as a region of the protein had some residues that were involved in catalysis and other residues that were involved in specificity. To a certain extent, these numbers are going to be a numerical representation of some of that. It's worth thinking about because we're going to see examples where the kinetics of an enzyme significantly affects how it can function biologically in a particular system. We're going to talk a little bit about inhibitors, the sort of the garden of inhibitors and what kinds of things can do it and how they work and their measurements and so forth. And we're going to talk a bit about allosteric regulation from a kinetic perspective. So let's start with something simple. We're going to start from, I need to fix this, don't I? No, sorry. I do wish they make this a default, but there you go. So we're going to start with one compound, A, that's going to turn into another compound, B. And this particular pair of compounds is extremely important because this is part of glycolysis, the metabolism of glucose. And we're going to see this reaction again, very definitely, not just there. But it means we can represent this reaction in a simple sense as A goes to B. And that's all that's going to happen. And in a simple reaction where you have only a precursor and a product, then as the product appears, here's your straight line, the glyceraldehyde disappears. And we can call V the velocity of the reaction, the rate at which either this appears or that disappears. So we can speak of the rate of reaction. How fast it appears, how fast it disappears are both ways of looking at rate. And so if we want to do that, we can say that the mathematics behind that is fairly simple. If you have just A going to just B, then the velocity will be the derivative of A at a unit of time. So in other words, this is the infinitesimal thing you did in calculus of a very little bit of change over a very little bit of time, which we can express as a rate constant. So the K becomes a rate constant, and you can multiply the concentration of A times that rate constant to find out the velocity at which that reaction is happening. So it's a fairly easy thing to represent. However, if you have a more complicated reaction, so here we have A and B are needed to go to C. In this case, the velocity is going to be the disappearance rate of A or the disappearance rate of B, and the constant is now going to be times both of the substrates rather than just one of them. So you can affect the rate of the reaction by affecting either one of those components. So the rate is now has two determinants, not just the one. If you start with a situation where you have vastly more substrate than you have enzyme, when you have substrate in excess, if you add more enzyme, the reaction will go faster. So if you have much more substrate than enzyme, your velocity is just going to be proportional to the enzyme concentration. And so that's a reassuring thing that there is some domain in which that would be true. But then if we hold the concentration of enzyme constant, if we don't vary the concentration of enzyme, but now we're going to look at concentrations of substrate, we're going to look at a slightly different situation. At the very lowest concentrations, there'll be, at zero concentration, there'll be zero velocity. And as you start to add substrate, so this axis down here is this concentration of substrate. As you add substrate, the relative velocity will start to rise. But it'll then start to peak off. It'll start to approach some value as an asymptote. And we've seen that curve before, right? That looks like the myoglobin oxygen binding curve. It's called a hyperbolic curve. And so in the previous slide, we were holding the substrate concentration maybe over here somewhere. And if you add more enzyme, it'll go faster because you've got more enzyme to do it. But if you hold the enzyme constant, what's happening is that those enzyme molecules are working as fast as they can to turn substrate into product. That's the maximal rate that they can get to. And you can represent that in sort of a three-step process. This is one way that people started to think about it that turned out to be very fruitful. The enzyme plus substrate can make an enzyme-substrate complex, and that enzyme-substrate complex has to go through catalysis and then release the product and restore the enzyme for the reaction to be complete. So this is a very simple representation of the simplest reaction you can think about with enzyme catalysis. This is a hair trigger mouse. So if we look at this as a function of time, in this particular one, what we're looking at is a reaction where we're going to start with a fixed amount of enzyme and a fixed amount of substrate, and we're going to watch how the various components of it change with time. So what we see is that the substrate is decreasing with time. It doesn't start right away, and so this sort of initial plateau is the time it takes for the enzyme to start to react with the substrate or to bind it. But it's decreasing in a linear way through most of the length of that time period and then tapers off. Complementarily, the product takes a little while to get started because the enzyme has to get occupied, but then once we're at steady state, you can see the product being formed and so on. These other two lines are a little different. So at the beginning of the reaction, we have some concentration of free enzyme. After some period of time related to the rate constant, we can reach a steady state at which some fraction of the enzyme is occupied with substrate as an enzyme-substrate complex, and the rest of the enzyme is unoccupied, waiting to collide productively with the substrate or the product, depending on the reaction. So at any one moment after we get past here, we actually have four species here: free substrate, free product, enzyme, and enzyme-substrate complex. And what that means is we can represent those motions in equations that look like this. The enzyme plus substrate has some rate, K1, at which it is going to make the enzyme-substrate complex. The enzyme-substrate complex at this point has two choices, to speak anthropomorphically. It can either go ahead and make product, and that would be K2, the rate of the second step, or it can fall back into enzyme and substrate. It can be unproductive, and that's the reverse K1 or K minus 1. So this shows you what the possibilities are for that enzyme complex. Either it's going to be productive or it's going to fall apart and it'll have to try again. And with those in mind as the options for the molecules and with these rate constants, we can think about this in a little more detail. So the rate of the equation, or the rate of the reaction, is, we've seen this before of the derivative. It's going to be proportional to the concentration of the product there at times K2 times the ES. In other words, here's the concentration of the enzyme substrate complex, and K2 is that forward reaction producing more product. So this is saying that the product is increasing in time as a function of that forward rate constant and the concentration of the enzyme substrate complex. Another way of then looking at this is that the enzyme substrate complex will change in time by thinking about all three of those steps. It will change when you go from free enzyme and substrate with K1. That'll make more of the enzyme substrate complex. There'll be less enzyme substrate complex when it falls apart. That's the minus K1. And there'll be less enzyme substrate complex when it makes product, K2. So these three terms together can determine the rate of change, if you like, of the enzyme substrate complex. The math on that looks hairy, not just to you, but to most people. And so enzymologists have come up with simplifications that if we look at reactions where the concentration of substrate is a great deal more than the concentration of the enzyme, then we can simplify things and say that the rate of change in the ES will be 0. And so we can get one of the terms out of the way by choosing conditions where it'll cancel out of the equation. There's more derivation going on in the book, and for those of you to whom mathematics is a beautiful language that clarifies people, I warmly recommend it to you. It's one of the clearest descriptions I've seen of the derivations behind kinetic equations. I'm going to skip to the punchline and try to convey to you the qualitative sense of what's been derived through those equations. They're called the Michaelis-Menten equation because Leonore Michaelis and Maud Menten were the two scientists who came up with it. And Maud Menten was, as you might guess from the name, a woman. So the core equation for enzymology comes from the first part of the 20th century with one of the two people involved being a woman. Michaelis constant Km, now this is a capital K there, right? Capital K there, is defined as, so it's not, measured to be. This is a definition of it. Michaelis constant is going to be the ratio between the things that break up the ES complex. Here's K minus 1, that's the ES complex falling apart back to substrate. Here's K2, that's the ES complex making product, over the rate at which it's produced. And so the Michaelis constant is looking at the tendency of that ES complex to form. And it's possible to relate that Michaelis constant to velocities if we know the other properties about this enzyme. So the velocity of a particular circumstance is going to be proportional to two things. It'll be proportional to Vmax, and Vmax is the rate at which an enzyme goes when it's completely saturated and going at top speed, maximal velocity, times the substrate concentration, over, or inversely proportional, to the Michaelis constant plus the substrate concentration. So the Km is going to enter into it, but the substrate concentrations will as well. And what we're going to do is we're going to look at what happens to this, the V0, when we modify some of those concentrations and values. It turns out to be the case that the Michaelis constant equals the concentration of substrate that will produce half maximal velocity. So this is in the ballpark with pKa's where you're half protonated and P50s where you are half occupied with oxygen, hyperbolic curve, Km, you're going at half your maximal rate. Or another way of thinking of it is half the enzymes have substrate on them, occupying them. It's approximately equal to affinity. And we say approximately equal because in most cases the efficiency of converting S tends to be enough different that what we're looking at is at the selecting of it. If the forward rate from ES complex to product is significantly smaller than the rate at which it tends to fall apart, then the Km is a reasonably good measure of affinity, the tendency of the enzyme to be saturated. And so when those conditions are met, when those properties are true, we can say that the Km is approximately equal to the free enzyme and substrate over the complex. Any questions so far? There are some other numbers that can tell us things about enzymes as well, besides the Km. There is a number called Kcat, for catalytic constant, and it is proportional to the maximal velocity and inversely proportional to the total enzyme. And so the Kcat is a way to measure how fast it goes when it's saturated. It's also sometimes called a turnover number because it's how many substrate molecules the enzyme can turn over per second. So the units are per second. It's a number per second. But if you think about this a bit, you can see that neither Km, which is measuring affinity, nor Vmax, which measures how fast it goes, or kcat, how fast it goes when occupied, is a complete description of how good an enzyme is. You can have a very good affinity for a substrate, but not go very fast. Or you might be able to have an incredibly fast velocity when you're occupied, but it takes a huge amount of substrate to get you there. And so the enzymologists have come up with a number called catalytic efficiency, which is the ratio of those two things. The ratio of the catalytic rate, which is a measure of how fast it can go when it's saturated, and the Km, which is the Michaelis constant. It measures affinity. That's the concentration of substrate that'll keep it about half saturated. And so this number, catalytic efficiency, gives us a single number that allows us to compare one enzyme to another as how good an enzyme it is. When you do this, it is possible to measure these things and to discover there are some enzymes that are such good enzymes that they basically catalyze a reaction every time the substrate hits them. They are what we call limited by diffusion. That it's just a question of how fast the substrate can get to the enzyme of how fast it can go when it's saturated. I have here this little side remark of an enzyme that's faster than diffusion, which if you think about this is sounding a little strange. Superoxide dismutase is one of the enzymes that protects our body from oxygen radicals. And it has an electrostatic surface on it that orients the superoxide and sucks it in like a tractor beam. And so when you measure the catalytic efficiency of SOD, it is actually faster than it could be by diffusion alone. So, any questions? Okay. So how do we measure these numbers, Km for the affinity, Vmax for the maximal rate? Obviously, we could have, wrong way. We can obviously have a graphical approximation by sort of eyeballing something like this. But the difficulty with that is this hyperbolic curve doesn't actually get up to Vmax. It gets closer and closer as you add more substrate, but it's a nuisance to try to do it that way. And if you don't know Vmax, then you don't know half Vmax, and so you don't know the Km very precisely. So just using a graphical method using the straight hyperbolic curve, the simple direct hyperbolic curve, obviously you don't have straight hyperbolic curves, turned out to not be very useful. But there are ways that you can transform these equations so that we do have a linear representation. And try to follow me through this because this is a really very powerful tool for looking at enzyme behaviors. We talked already about this equation that V0, the velocity of that enzyme at a particular condition, is going to depend directly or positively on the Vmax, how fast it could go if saturated, inversely to the affinity. The bigger this number, the less it takes to make it go, and proportionate to the substrate here and the sum with the Km down there. If we were to rearrange this, we discover that we can rearrange it into this form. So 1 over the velocity is going to be equal to this number, Km over Vmax, times 1 over the substrate, plus a constant term, 1 over Vmax. So 1 over Vmax is a constant. This is something that can vary as you vary the substrate concentration, but this is a constant in front of that. It's a slope. It's the slope of the line that we're going to draw. So if you can sort of cross your eyes and blur your eyes a bit, what we've done is create an equation in the form of y equals mx plus b, which is a homely old Algebra 1 equation for a straight line. And the slope here will be the ratio of the affinity and the Vmax. and the intercept will be 1 over the Vmax. And in practical terms, what that looks like is this. It's a graph called a double reciprocal plot. That is, 1 over V0 is a reciprocal, 1 over substrate is a reciprocal. And you can get a certain number of points by measuring your enzyme activity at several different concentrations. The slope of that line will be the Km over the Vmax. The intercept with the x-axis is 1 over the Km. The intercept with the y-axis is 1 over Vmax. So now we have something that should give us a straight line that we can then extrapolate more directly to obtain Vmax and Km. And it's easy enough to keep straight which of these is which, because the vertical axis is the reciprocal of the velocity. So it's not surprising you're going to find the reciprocal of the Vmax there. And the horizontal axis is the reciprocal of the substrate concentration. And 1 over Km is telling you something about the substrate concentration for half saturation. This is sometimes called a Lineweaver-Burke plot, after the people who realized that you could do that. It also makes it much easier to compare one enzyme to another, because you have now a straight line, and it will turn out to be simpler to look at these things. Let's see. Yeah, okay. Not a whole lot of biochemistry happens with reactions where A goes to B. It would be a simple world if we did that, but we probably wouldn't be very exciting people if it were true. It's much more common to have multi-component reactions, and this is just giving you a sample of something like that. Here's one possible reaction where you have X, which is an oxidized molecule, and Y is a reduced one. And at the end of the reaction, it's now X that's reduced and Y that's oxidized. So they've transferred electrons from one to the other. Or here's an enzyme called transketolase. And what transketolase is going to do is take a 6-carbon sugar, chop off 2 carbons from its head, and plant them onto a 3-carbon sugar. And now we have a 4-carbon sugar left here and a 5-carbon sugar over there. We're going to see transketolase a lot when we get into carbohydrate metabolism. So clearly this enzyme has some kind of an affinity for fructose 6-phosphate and has some kind of an affinity for glyceraldehyde 3-phosphate. As a consequence, it has 2 Kms. It has 2 Michaelis constants. You have to be able to describe the affinity for everything it's going to bind, and so it has more than 1 Km. You can even break this down into a little more detail. So if we let the little half moon here be the enzyme, we can look at the different steps that have to happen. You have to bind a molecule of fructose 6-phosphate, and this step is the first one we talked about before of making an ES substrate complex, which could fall back to the original. But if this proceeds forward, we now have an enzyme intermediate complex, if you like, with the 4 and the 2 carbon fractions on it. From that shape, you can either produce free erythrose, and the forward reaction from here would making the erythrose and the 2-carbon fragment. The back reaction would be to simply close that back up again, because energetically it can. If you have the complex with a 2-carbon fragment, it can go backwards again if there's erythrose around, or it can go forward by picking up a glyceraldehyde 3-phosphate to make an intermediate state now that it has a 2 and a 3-carbon piece. That again has a forward and back reaction. The 2 plus 3 complex has a forward and back reaction. And this enzyme substrate complex can either go forward and release the xylulose or go back and break it into 2 pieces again. So you can see there are a lot of rate constants. Every arrow there is a rate constant. And there are people who spend much more time than I would have expected measuring each and every one of those rate constants. Nonetheless, we can talk about a kcat, or a Vmax, by talking about the overall reaction of the overall rate of starting with fructose 6-phosphate and ending with xylulose 5-phosphate. So you can collapse all of those different rate constants into one catalytic constant. So far we've been talking about enzymes that are simple, direct kinds of reactions that have hyperbolic curves. The enzymes with the hyperbolic curves are well described by Michaelis-Menten kinetics for the most part. But there are some other enzymes that don't look like that. And they unfortunately tend to be the enzymes that are very exciting and interesting to know about. So if we have an enzyme like this, here, again, you have substrate concentration on the bottom, you have velocity on the vertical axis. In this case, adding more substrate doesn't change the rate very much. Then we have kind of a linear range, and then it tapers off again. This is our old friend, the sigmoid curve. And just as hemoglobin, we had a sigmoid oxygen binding curve that indicated that there was cooperativity. A sigmoid curve for an enzyme also indicates some kind of cooperativity going on. That there can be crosstalk across the enzyme to make other parts of it behave differently. Almost all examples of sigmoid kinetics are in multi-subunit enzymes with at least 2 subunits. We'll see one in carbohydrate chemistry where seems everything happens, of a monomeric enzyme that manages to do this, but that's an extremely rare thing. Usually this is a clue that what you're looking at is a multimeric enzyme, just as hemoglobin was a multimer. The numbers are still going to have a similar meaning. So you can talk about a Vmax, how fast the enzyme goes when it's completely saturated. And you can talk about a Km, the concentration of substrate it takes to half saturate that enzyme. So at the Km, when the concentration of substrate's equal to the Km, about half that enzyme will be occupied. Any questions so far? So let's think, I keep forgetting that clicking makes these things go forward. So far we've talked about enzymes going along hunky-dory, catalyzing reactions, as if they have no cares in the world. But it turns out that both in biochemistry itself, in metabolic pathways, there can be examples of inhibition. Also in things like agriculture or medicine, some of the most important chemicals are enzyme inhibitors. So it turns out to be worthwhile to think about enzyme inhibition as well as enzyme kinetics. And there are a number of different kinds of enzyme inhibitors. Some of them are actually irreversible. These tend to be molecules that share some structural similarity to the normal substrate, but have on them a reactive group that can make a covalent bond to the enzyme. Typically at the active site, sometimes somewhere else. We sometimes call these suicide substrates because they bind and they're gone. They're never going to do anything else in their life. And so here's one we've already talked about in the past. Here's chymotrypsin with its active site. And DIPF is an analog of a peptide bond. But because of the floral group, you have the capacity to make a covalent attachment at that stage where you have the covalent intermediate in the normal reaction. It makes a covalent intermediate and then it doesn't come off. And since once it's lost the fluoride, it's stuck on there, that molecule is not going to catalyze another reaction. Here's another example of a suicide substrate, one that has very great significance, 5-fluorouracil. So here is the uracil molecule, and it's 5-fluoro because it has a fluorine instead of a hydrogen there. Otherwise, you can see the rest of the structure is like uracil. It's enough like uracil that the body starts to treat it as if it were uracil. And so there's an enzyme called thymidylate synthase, which is normally used to take deoxyribose 5-phosphate UMP, so this would be the uracil hill, and add a methyl group to it to turn it into the thymidylate monophosphate. So this thymidylate synthase has to add a methyl group at the 5 position. this has a fluorine there. And so as a consequence, when this thymidylate synthase attempts to use the fluorouracil, it sticks and stays on that enzyme. Now, if you think for a little bit, obviously thymidylate synthase is essential for making DNA because you need to have thymidine to make DNA. And so by poisoning this one enzyme, you're going to poison cell division. And since cancer cells tend to be more rapidly dividing than other cells, you can preferentially target cancer cells. It's not a perfect exclusion. Another form of inhibition is competitive inhibition. We saw how the suicide substrate had to have some resemblance to the substrate to get in there, but then it made a covalent bond. If it didn't make a covalent bond, if it could bind at the active site, but didn't poison it permanently, it would be likely to be a competitive inhibitor. And diagrammatically, that's what this looks like. You have some enzyme, its normal substrate is the pie-shaped thing. The pie wedge thing. The kite-shaped thing is a competitive inhibitor, which clearly shares these structural features and can fit into the active site, but it's missing whatever that curvy surface was that allows the reaction to proceed. So whenever the inhibitor is sitting in the active site, the enzyme can't be catalyzing a reaction with the substrate. Competitive inhibitors simply take up space on the enzyme's active site and prevent the real substrate from getting anything done. Kind of like someone who's staying on the phone listening to a busy signal but won't let you die. Although I guess there are no pay phones anymore, are there? Okay, so what does this look like? What does this look like in kinetic terms? And I apologize for the red-green. Your textbook used it. I tried to find a comparable diagram without it. At least they're labeled. So the upper green line here is the normal kinetics of that enzyme. They're getting a little dramatic here and showing it pretty close to the Vmax, but you know, artistic license. If this is the Vmax, then at the half of the Vmax, we look here and go down to the horizontal axis. This is the Km of the enzyme in the absence of the competitive inhibitor, the uninhibited reaction. But if we add some inhibitor, now some fraction of the time, the active site will be occupied by inhibitor instead of by substrate, and it can't catalyze a reaction. But we should be able to overcome that by adding more substrate. If down here, you know, it's a 50-50 probability of having a substrate versus an inhibitor, if you add more substrate, at some point, you're almost certain to get substrate instead of the inhibitor because there's so many more substrate molecules. And the way we represent this mathematically is to say that the Vmax does not change from a competitive inhibitor because you can add enough more substrate in principle to get it back up to its original Vmax, which is also telling you that the catalytic constant is not changed. It hasn't harmed its ability to actually make a reaction happen. All it's doing is taking up the active site when there's enough of the inhibitor around to be a reasonable competitor. And so this turns up as a change in the Km. You can see here that the Km is now maybe 4 or 5 times as high, or it apparently has less affinity for the substrate. In fact, that's not the case. It's the enzyme that's sometimes occupied by something else. And so if you add enough substrate, you do eventually get the reaction back. Why don't we call a break there, and we'll see you on Wednesday. I'll be posting that PowerPoint I started the class with on Icon if you want to see those slides again.